Is it running? Oh, it is, sorry. Yeah, we did this for a public talk. I thought it was really fun. So, a demonstration that the lid matters. This is cream at the bottom of a teacup, right? And she's putting ice cubes on the lid, cooling it off, moving things to 2 AU, increasing the temperature gradient. It's the lid that matters. And convection is more vigorous. Okay, so there's greater heat transport. In this case, also mass transport. So the temperature, not the density, but the temperature matters. The outer boundary temperature matters. The most amazing thing about this experiment is that it was done by a theorist. It took us forever. Okay. Okay. These planets, the problem is, they're not found at 2 AU. Right? They're not found at 2 AU. They're found at 0.2 AU. So now we're stuck. Now we have to appeal to migration. Well, I don't know any other way to do it. But a signature of migration, as I indicated earlier, is resonance. Right? You can lock yourself into resonance. And so I find it encouraging that in every case that we've tracked, the super puffs, there aren't that many of them, but every time you find one, they're in resonance. And not only that, they're preferentially the outer links of resonant chains. So I find this encouraging, although people love to tell me that I'm hopelessly biased. And I know I'm biased. Of course I'm biased. In every sense of the word. But the bias here, right, is that the super puffs, the only way to detect them so far is through TTVs. And TTVs favor resonant systems because the amplitude of the transit time variation is largest for resonant systems. How else are you going to get at these tiny little nuggets of 2 Earth masses? It's from TTVs. So yeah, there is a big selection bias. Again, one can only point to tests and hope for a larger sample of these objects and test the idea that they're preferentially in resonance. I will remind you that super-Earths are mostly not in resonance. Yeah, I know there's some little bit of excess here at 2 to 1 and 3 to 2. I consider these secondary effects, just a little bit of dissipation, a little bit of gas, and you can wedge them out a little bit. But most of them are not in resonance, okay, which points naively, and I think truthfully, to an in-situ formation. Okay, what does planet formation look like in the post-Kepler era? It looks like what Alma's seeing, okay? And what Alma's seeing is amazing, as you know from all the work being done here. I think at this point, the images look more interesting and richer than the theory. The gaps, I think a good case can be made that they really are carved out by planets, as I'm sure people here recognize as part of the D-sharp campaign. Here's our stab at it. I think we find quite consistent results. The double gap here, seen in HL tau, we think we can, both of these gaps we can reproduce with a sub-Jupiter out there at 70 AU. It's interesting that the viscosities required to produce this fine structure are on the low side. Okay, this, I think, is where the whole community is moving towards. We're recognizing that the alphas, the Shakura-Sonyaev viscosities, are all low, less than 10 to the minus 4. For high diffusivities, you just blur out all this structure. You can't reproduce it. But we're looking at nearly inviscid environments. Now, if you throw a core of mass 10 Earth masses into one of these gas-rich systems, that's disaster for the cooling theory. As I answered in answer to Dave Wilner's question, you undergo runaway. What is runaway? Runaway is when it's triggered when the mass in the atmosphere becomes comparable to the mass in the core. At that point, you can no longer neglect the self-gravity of the atmosphere. Okay? And to hold up this heavy thing, in radiative and hydrostatic equilibrium, you need to jack up the luminosity. But if you jack up the luminosity, the cooling rate goes up, which means you accrete more mass. And now you're in deeper trouble. And so it's a catastrophe. Runaway is a cooling catastrophe. And it's an open question why it is, that this instability, it's unknown. What stops it? Why should it stop at a Jupiter? Or any other value? Sub-Jupiter or sub-Saturn? Why should it stop? This is an open question. Almost certainly, I think it has to do with the opening of gaps in disks. These gaps, by the way, right, they're not open because the planet is consuming the material. They're open because the planet is wedging the material away from itself. Right? It's exciting waves. The waves carry energy and angular momentum. Where the waves break, they propagate away from the planet, and where they steepen and break, just like ocean waves, they release all of that momentum to the gas and nudge it away from itself. And so this is a way in which you can limit the final masses of gas giants. This is work we just submitted with Sivan Ginsberg, postdoc at Berkeley, and he can derive an analytic expression, actually, using the gap opening theory to derive a final mass in nearly inviscid environments, which encouragingly at 10 AU is about a Jupiter, and it grows with increasing distance. So the farther out you go, the larger the maximum mass. Okay, so we submit this as a possible test for observations, is that the characteristic masses of gas giants as you move out should grow. And here's my last slide. So plotting occurrence rate versus period. It's just amazing to me that people can make plots like this. It's just so inspiring. It's so great. What is being plotted here? The cool colors are the super-Earths, sub-Neptunes, the small things. The warm colors are the gas giants. So I've overlaid on this. I've attached to the RV and transit data the results from direct imaging. So I'm part of the GPI collaboration, and we just submitted a paper which reports on occurrence rates for giant planets outside of 10 AU. And this is pretty much what the line looks like. And a beautiful plot like this deserves to be completely messed up by theory. So I'm going to overlay on this my theoretical prejudice just by way of summary. Small things, in situ, yeah, there's a little bit of migration from tides as you get really close in. But it's mostly an in situ story, late. For giant planets, not the case. Early, gas-rich systems, plenty of lines of evidence that things move around. Where are they created? Well, the observations seem to indicate sort of a sweet spot for giant planet formation, which is between about 1 and 10 AU. Sweet spot, over here. Plenty of unsolved problems. I've talked about major mergers. Well, that doesn't work. That just doesn't work for core formation for giant planets, right? There's just too much gas, too much dynamical friction. So it's not major mergers. It's got to be minor mergers, otherwise known as pebble accretion. So aerodynamics starts to matter. So how does that play out? The distinction between minor, how does you decide between the minor versus the major channels? This depends upon the first doublings, right? Planetesimal formation, very much an unsolved problem. I've talked about the last doublings in mass, but the farther back in time you go, the hazier it gets. So that's that problem. And finally, there are dependencies of all of this data on stellar mass, which I'm currently thinking about. So that's it. Thanks.
Thank you for the fascinating talk. We have got time for just a few questions.
I was struck by this plot because if you put binary star systems, they would pretty much be in line with the directed image of Jupiter, right? Because you have roughly of all the unity per log period. And so you will fill up everything to the right, roughly at the point where you have your dashed line with binary companions also.
You're talking about stellar binary
Stellar,
companions.
yeah.
Well, I mean, I could comment a little bit tangentially to that. If by that similarity one is thinking that maybe giant planets and stars form the same way.
No, not
Okay,
necessarily, but they
okay.
affect each other.
Okay.
You cannot ignore the
I see,
binary
I see, yes,
aspect.
yes, I
You
see,
cannot
I
just
see,
think
yes.
about Jupiters without
Yes.
thinking about binary.
Okay, sure. Yeah, I mean, there are other comments I can make about there's a line you can draw for brown dwarfs too, and it's lower by about an order of magnitude, and it goes up. It slopes up. That's also the result from GPi.
Well, why did the Earth not accrete a modest envelope of hydrogen? Is it that it's too low mass, it grew up in a gas-depleted environment, or it did and we lost it? Those are all.
Yes, the Earth didn't accrete an atmosphere like the super-Earths because it was born in a low surface density solid disk. So you have to, I have to posit here that disks, they have solid surface density, sigma solid. There's a whole range of sigma solid. Most disks, apparently in the universe, 50% of them, have sigma solid so high that they can breed super-Earth cores fast and early.
Yeah.
Okay. In the case of the Earth, we were born in a disk where sigma solid was so low, major mergers still happen, but they happen over a longer period of time. Try 10 to the 8 years, okay, when there's really just no gas around.